All right. So hi everybody. Yeah. So last lecture, I introduced. So yesterday, I introduced the notion of Euler hydrodynamics, Euler scale hydrodynamics, in particular the Euler scale scaling or the Euler scaling to obtain the hydrodynamics and the idea of local thermalization. Now, I think we had said yesterday that there might be questions, so we might want to do a question session before we start. So, are there any specific questions about last lectures?
Are there any questions? I think, Benjamin, there were no questions.
Yeah. Okay, so yeah. So one thing, so I will. Well, one thing is that it might be interesting to give a little example actually before I start with the states and the generalized Gibbs ensemble. So it's a small example of a calculation you might do. So I didn't give the tutorial problems yet. I'm sorry about that, and I will do that. But one nice problem, small problem that one can look at is something that I said. I said here are general kind of principal equations, and if you look in Galilean system, then you can see that they reduce to those that I wrote at the beginning that you find in standard textbook. So there is a, let's see. So I just give example here. So if you have a Galilean system, so again, the Gibbs states are of the form exponential minus beta h minus mu n minus mu p, okay? But you have to take an explicit system to calculate something out of that, right? You can calculate the quantities that I discussed last time, for instance, for free particles. So that, ideal gas, if you wish, ideal gas in one dimension, right? So for free particle, things are relatively simple. Let's say one can take classical or quantum, essentially it's the same form. And what you find is that you have the conserved quantities, which are the energy with conserved density h, the momentum, the number of particles. And in order to argue with the notation that I have later, I'm going to call this one Q2, this one Q1, and this one Q0. They have explicit form, right? So, for instance, Q0 of x is so-called empirical density, sum over all the particles, and delta x minus xn. And Q1 is the momentum, so sum over all particle n, Pn delta x minus xn. And if you have free particles, Q2 is relatively simple. Free classical particles, you just have the energy. Can you take energy? Because there's no potential energy. So Pn squared over 2. And that's it. So these are your averages. And the Gibbs state is explicitly quadratic. This is quadratic in the momentum. And it's you can put an external potential, you can put it in the box, you can make it well defined. And from this you can calculate conserved quantities and conserved densities within that Gibbs state. So the results for free particles are relatively simple. If you calculate the average of Q0 within the Gibbs state, you find essentially you find that it will have the form integration over all the momenta, and then some function which is the distribution of the particles over the momenta, f of p. Now f of p for free particle will have very specific distribution of the type exponential minus p squared over 2. With some normalization, make it proportional. And, well, not exactly p squared over 2. Actually, maybe I should use that. There's also there's a Hamiltonian and there's a momentum there. So there's going to be minus beta p squared over 2 minus vp. So that's Q0, and you can also calculate Q1, and that's going to be integration dp, pf of p, and Q2, integration dp, p squared over 2 f of p. So it's relatively simple. And this is a good exercise to try to calculate, I mean, it's something that you can find in the textbook, try to calculate these average densities of particles, momentum, and energy in a model of free particles where you have a Gibbs state and connect that with this distribution and these things. Now, I said that we have conserved currents as well, and these are essential for the hydrodynamics, right? So if I do dt q0 of x, I can do it explicitly from the expression here, right? And I find sum over n with a minus sign x n dot delta x minus xn. But since I have free particle, x n dot is equal to the velocity, is equal to the momentum taking mass to be 1. So this is nothing else but minus sum over n pn delta x minus xn. Sorry, with the prime here, with the prime derivative of the delta function. And you see that this is exactly the derivative with respect to x of q1. So I find this is minus dx q1 of x, which is indeed the conservation laws that I wanted, right? So dt q0 plus dx j0 equals 0 if I set j0 equals q1. So indeed, I have a conservation law. And you can do the same for dt for finding j1 and for finding j2. And you see that they are actually directly given in terms of the densities q1, q0, q1, q2. Well, g2 is slightly outside of that, but g1 is still given in terms of density of energy. Okay? So you can find expressions for g1 and g2, and then you can find their averages also. So the average of g0 is equal to the average of q1, and that's integration dp p f of p. Likewise, the average of j1 is integration dp p square f of p. And the average of j2, the energy current, that's integration dp pq over 2 f of p. So basically what you see is that you just have to take these expressions there and multiply inside the integral by p to get these expressions there. This is very natural. It says that if you want to have the current, you just have to take the density and look at every particle of momentum p and multiply, how many particles you have of momentum p by p, which is the velocity, and you get the current. Okay. So this is for free particles, and it's a direct calculation from the Gibbs state and from the simple expression of Hamiltonian for free particle, which is just a sum over n p squared n over 2. And so we have explicit form for these things where f of p is essentially proportional to a shifted Gaussian. Okay. Now here are the things to check. If you take all these explicit form, you can check the following. You can check that the average of J0 is equal to the average of Q1. Well, there's nothing to check. I've already said it here, right? This is already there. But you can also check that the average of J1 has a form of some function, I called it P, some pressure function, that depends on the average of Q0 and the average of Q2. Well, here it depends in a simple way, plus Q1 square over Q0, the average of Q1 square over the average of Q0. In other words, the average of the momentum current is the pressure in the state where you have no average momentum, so no velocity. So the pressure in the rest frame plus a correction due to Galilean transformation. So this is pressure in rest frame, and this is just Galilean shift. This you can check explicitly from the formulas that I've written for you, basically from these, which are for free particles, but this is the general principle. And likewise, you can check that the average energy current, J2, has the form of 3 average momentum density over 2 average particle density times the pressure plus average momentum density cube over average particle density square. And again, this particular form is due to Galilean invariance and is a general principle coming from Galilean invariance. Right? But you can check that explicitly for free particle. And once you have that, you put that into your equation. So now you define rho as Q0. You define V rho as Q1. Right? And then you have the energy density. So let's say E as Q2. And you write the conservation laws, and you will find that you have dt rho plus dx v rho equals 0. And you will find the Euler equation. So dtv plus v dxv equals the thing that I had written in my first slide, okay, which I'm not going to write here because I'm surely going to make a mistake in the precise coefficients and everything. But the thing that I was written in the first slide, which is really what is usually called the Euler equation. So just directly from taking what I had written like in a general setting, you can apply this to free particles where everything can be calculated explicitly. And you find explicit form for the densities and explicit form for the currents. You put these explicit forms within the conservation law, which are so first of all, you realize that the currents can be written in a relatively simple way in terms of densities by using appropriate shift of momenta. This comes from Galilean invariance. So you find these relations. Okay? And it is important that you use the form of this f of p. It's not so important that it be Gaussian, but it's important that it be symmetric in around a certain value of the momentum. Okay? Here, which is not around 0, but around a certain value of momentum is symmetric. Okay? And once you have that, you put them into conservation law, which are dt of qi plus dx of pi, and then you get the standard equation of conservation of mass and Euler equation, and you get one more equation for the energy, which I did not write, or which you can write. Okay. So this is an example, and it's a good exercise to try to get these things there, okay, and to prove these equations as well. So to get the form of the currents in terms of the densities due to Galilean invariance, and to get the standard form of Euler equation and of conservation of mass, and the one for the energy as well. And then you get the equations. If you put explicitly these quantities, these currents, and these densities, you would get you would get essentially the one thing. Okay, so the one thing that's important. Once you do that, you realize that there's only one function that you need to determine, right? Which is the pressure. Pressure is the current. The pressure is the current in the rest frame. The momentum current in the rest frame. Pressure is momentum current in the rest frame. So once you know that, the momentum current in the rest frame, which is pressure, then you put that in this equation, and for any Galilean system, then you have the hydrodynamic equation. For the free particles, you can calculate this explicitly from the expression that I've given, and then you get the pressure for the ideal gas. And the pressure for the ideal gas, this is usually these are the equations of state of the ideal gas. Okay, so in Galilean system, the only thing that you need to know is the momentum current in the rest frame as function of average number of particles and average energy, and then you have everything. Okay? Now, of course, in the rest frame, the average momentum is 0. That's the definition of average momentum. So the pressure does not depend on the average momentum because it's momentum current in rest frame. Okay? The average momentum occurs on the second term when you are not in the rest frame. So it's Q1 squared over Q0. And it's just a consequence of Galilean invariance. The specific form is the way it arises is a consequence of Galilean invariance. And so that means you reduce the problem in a generic many-body system to the calculation of a single function of two variables, the pressure as function of mass density and energy density. And once you have that, you can write the hydrodynamic equation at the Euler scale for any Galilean system. Well, any, not quite, right? Because then we go to integrable systems, as I said last time, but for a generic Galilean system. And you can do this for the free particles and you get the equation of ideal gas. Okay. So this is I'll try to write it kind of down a bit more nicely. And this is a nice problem for you to look at and to do explicitly. It's an explicit calculation that you can do to get the Hydro equation for Galilean system and for ideal gas. Okay. Questions about that? So this was assuming, so all this was assuming that local thermalization or local relaxation was towards Gibbs state. So H minus mu n minus Vp. Okay. But as I said last time, in general, or perhaps, in general, we can have more conserved quantity. So Hamiltonian is conserved, number of particles is conserved, momentum is conserved, but we can have more conserved quantities, and this happens in integrable system. It could happen in other systems, but there are kind of general theorems and arguments that tell you that, in fact, if you have more conserved quantities of the Hamiltonian type involving higher power momentum, then you probably have infinite number of them, and then it's probably integrable. So, okay, so example in integrable systems. You have essentially an infinite number of them. So Q0, call it N, Q1 is P, Q2 is H, Q3 also exists, Q4, Q5, Q6, etc. Okay. What are these conserved quantities? So, the simplest example is the one that I just did now, free particles. Of course, the system of free particles is integrable. I mean, we know exactly how the trajectory is. There's nothing, this kind of, it's very simple. Xn of t is Xn of 0 plus Pn t. So we can solve the whole system. There's essentially nothing to do. And Pn of t is Pn, which is Pn of 0, which is constant. But this is okay. But what is interesting is the structure. It has conserved quantities of this type. What are these conserved? What would be Q3? So Q1, Q0 was the number of particle. So this is what I call N, number of particle here. N goes from 1 all the way to capital N. In a macro canonical ensemble, this is fluctuating. Okay. Q1 is the momentum, and that's the sum over all the particle of Pn. Q2 is the energy, and that's of course the sum over all the particle of Pn square over 2. Then what is Q3? Well, it's very simple. The whole point is that the momenta of the particles are all conserved. Particles go to each other without interacting. So actually, every single momentum of the particle is conserved. So I can write Q3 as, say, sum over n Pn cube, say. And maybe for notational, for good notational convention, I should say that Hamiltonian is Q2 over 2, right? And so that in general, then Qi is sum over all the particle Pn to the power I, for I being 0, 1, 2, 3, 4, etc., etc., etc. And these are, of course, all conserved. That is, I can take simply the sum of any power of the momentum, and because the momentum of each particle, and because of each momentum of each particle is conserved, this is conserved. Of course, I could have taken just momentum of particle 3, for instance. That is conserved. However, that would not be an extensive conserved quantity with a local density. These are conserved quantities which sum over all the particles and which have a local density. That is, I can write Qi as integration over all of space of some density Qi of x. And this density is local, so Qi of x just knows about what's happening around x, so beta x minus xn, and all I have to do is multiply by Pn to the power I. So these, okay, of course, I can take any power. I could not have taken just particle 3, because if I just do with particle 3, I could ask for particle 3 to be around x. However, the conserved quantity itself just for a single particle would not grow with the system size. Okay, I'll come back to that. For now, these are the natural conserved quantities. So you see that I have a lot of conserved quantity. In fact, I have a bit more. Given any function, f, from R to R, may be nicer than a function. So I can define Q for that function as being integration dx of the conserved density for that function. And the conserved density is nothing else but taking function of all the momenta, f of Pn. And because all the momenta are conserved, this is also conserved. So instead of taking powers, power 0, 1, 2, 3, 4, 5, I can take any function. So I have actually a functional space of conserved quantity. Okay. Now, what do I do with this, right? So the main idea is that all I have to do in order to treat the system of free particles in a hydrodynamic way, all I have to do is to do the same, to apply the same general principles as I had previously, but for relaxation that is not towards the standard Gibbs state, those that I have written there, not towards the standard Gibbs states, but instead towards the generalized Gibbs ensembles, so the state that involve all the conserved quantities available. Now, when I say all, I have to be careful, and I come back to that just now. Okay, but for now, I say all conserved quantities. In other words, all of these Qi. So, and this is kind of just physics principle, right? I do that a bit blindly without asking too many questions. I say it would be natural to involve all the conserved quantities in the local relaxation. Let me do that and see what I get. Okay. So I would say local relaxation is towards the generalized Gibbs ensemble. So these are the distribution with Boltzmann weight of the type sum over all conserved quantity bi beta I for some parameters Qi. So the beta i's are the so-called generalized inverse temperature. Inverse because it's beta 1 over T, but okay. They are associated to all the conserved quantities available. Q3, Q4, etc. So what is this explicitly sum over I, beta I, Qi? Well, I know for the free particle what it looks like because the Qi's, they have a simple form, have this form there, right? So this is sum over all the particle n, sum over I, beta I, Pn to the power I. So just to be careful here, this is beta I has index I, while here Pn has power I. It's just that I like to put the index on top for the betas because it's actually a covariant index instead of contravariant, or perhaps the opposite. So, okay, so I have beta i's with a lot of indices and this. So this is actually nothing else but sum over n of some function of the Pn, where f of p is just sum over I coefficients beta I and the ith power of p. Okay? So what I put in the Boltzmann weight for the free particles is sum over n of an arbitrary function f of Pn. And these are my generalized Gibbs ensemble for free particles. So I could write that explicitly, right? Explicitly, what are these generalized Gibbs ensemble? So you have in the macrocanonical ensemble, the macrocanonical is the generalized Gibbs ensemble in macrocanonical way. You'd have to sum over all the number of particles. You have to integrate over all the positions and the momenta. And then you have to put this Boltzmann weight, exponential, minus sum over particle function of the momenta. And yeah. Yeah, and if you do Boltzmann statistics, you have to put a 1 over n factorial. Sorry, now I'm a bit confused if you have to do that or not. But okay, so this is the partition function. Yeah. So standard partition function for free particle, except that for the Boltzmann weight, you put an arbitrary function of the momenta. Right? These are the generalized Gibbs ensemble for the free particles. And then you can calculate all the conserved densities and all the currents within that ensemble. Of course, you have kind of non-trivial functions, f that is involved there. Maybe I should call it, actually, not to confuse with my previous f, I should call it w. Sorry, w is my standard notation. W, okay? And so you can perform these integrals. There is okay. So for instance, I can try to calculate the average of Q. Oh, okay. One thing I should say. Sorry. Be precise. Right. The integration over the x's must be in some finite volume. Let's say from minus L to L over 2, say. This physically represents the fluid cell, essentially, right? So you constrain the x's to be finite volume, and then you can evaluate thermodynamic quantities by taking the large volume limit. For instance, the free energy would be the limit when L goes to infinity of 1 over L, the log of Z. Now, Z depends on L. Okay? It depends on L, right? And that's now depends on what you put for the generalized Gibbs ensemble there, what function W you put here. But this can be evaluated by various techniques. Okay? So this was, maybe I leave that as a problem. There's some various techniques to evaluate that. Okay? Just so in the case where W is quadratic, you get Gaussians, then this is the case of the so-called ideal gas, assuming that you have just normal Gibbs ensemble. But in general, you have generalized Gibbs ensemble and you have a generic W. Okay. Now, this is somehow, this is what I do, the system of free particles. I notice that there's a lot of conserved quantities. I then look at what relaxation can be. Well, is the generalized Gibbs ensemble that involve all the conserved quantities. I can write quite explicitly the partition function, the measure for this generalized Gibbs ensemble. And then I can calculate, then I can do the procedure that I explained to get hydrodynamics. So to get hydro, procedure is like that. Calculate the QIs and their current JIs, And I know all the density and the currents for these free particles. Within these states, that depends on all these betas, all the betas there. So the state that depends on the betas, I put beta with a little bar underneath to say that this is a lot of them. So beta bar is beta 0, beta 1, beta 2, beta 3 is a vector of all these beta. Okay? So I have to calculate all the densities, all the currents in a generic relaxed state, a state that depends on all the betas. And then I have to write the conservation laws. So I assume that locally the system goes to that, and I write the conservation laws. And these are dt qi's of the betas. Now all the betas depends on x and t, right? Plus dx of the current that depends on beta that depends on x and t. And naively, I mean, without proper derivation, right? Just applying principles of hydrodynamics, I say that this would be a good description of free particles at the large scales. So use the principles of hydrodynamics, but use not just thermalization to Gibbs state, but thermalization to generalize Gibbs ensemble, which here, generalized Gibbs ensembles are simply take the usual Gibbs ensemble and replace the Boltzmann weight as function of momenta by, instead of being a quadratic function, by an arbitrary function of momenta. For free particles, this is what it is. And this is, in principle, that's the hydrodynamic equation for free particle, the Euler hydrodynamics equation, in quote, for free particle. Now, notice this is not the ideal gas hydrodynamic equation, because the ideal gas assumes that you thermalize the Gibbs state. Then it assumes that you have no interaction, and then you write the currents and densities in terms of no interaction, like I did just at the beginning of this class. But it says, you have still a Gibbs state. Here I'm saying, no, because you have all these conserved quantities, somehow you should include them in your thermalization, right? So as you thermalize, other conserved quantity of the Hamiltonian type should be involved in Gibbs state. And that should be the equation. Okay. Now there are two things then I want to do here is this the right equation? What does the equation look like, first? And second, why do I have to involve all these conserved quantities? What conserved quantities exactly should I involve? What is this? What are these generalized Gibbs ensemble, right? What is this relaxation to all these, to this kind of bigger set of state, right? So there's two things then here that I want to say. Before I say that, are there any questions about what I've done till now?
May I ask a question?
Yeah.
So, this is probably pedantic. When we talk about GGE, the Generalized Gibbs ensemble, sometimes it's assumed that there are an infinite number of conserved charges. But strictly speaking, that is only true when the number of particles itself is taken to infinity first. Yeah. Otherwise, there can at most be n, capital N number of conserved charges. So I just wanted to, what should be done more generally? Perhaps just to take large N limit to begin with. Is that?
Yeah. So I mean, this is a very good point. I mean, yeah. I mean, I glossed over a few things here, right? So since I'm thinking about macrocanonical ensemble and I'm summing over all number of particles, then I'm justified to say the infinitely many number. So indeed, actually, what I did is exactly as you say. I did take number of particles to infinity first.
Okay.
Of course, I control everything by taking a finite L, so it's okay. But I take particle to infinity first. Yes. And if you then why is it good? I mean, if you have a quantum chain, for instance, you take finite number of sites, you don't have infinite number of conserved quantities again, right? You have finite number and all that. So this is true in all cases, yeah. And so it depends on the application that you have in mind, actually, right? So for non-equilibrium physics in particular, for hydrodynamics, the limit of infinite number of particles is a priori taken when you do at least Euler scale hydrodynamics. Then you can wonder about correction due to finite number of particles finite volumes and all that. That's another problem, right? But if I'm directly at the earlier scale, then okay, I've got to have infinite number of particles because I want finite densities and infinite volume, infinite variation scale. So I have to have infinite number of particles, and then I do infinite number of conserved quantity. Now, this being said, in practice, when you look at what happens in the integrable models and you do generalized Gibbs ensemble, typically it's sufficient to consider first few conserved quantities organized in the right way. You have to organize them like the first, second, third. First few gives you a good approximation of the state. So there is a notion of convergence in this infinite set of conserved quantities. There's conserved quantities 0, 1, 2, 3, blah, blah, blah. Right? And the way that I've written here is not amazing because I'm assuming, if you wish, convergence as a Taylor series for this function W of P, right? Well, in fact, it might not be convergent as a Taylor series, but maybe if I take the right basis of function, this notion of conversion. And then you have your finite number of conserved quantities appropriately chosen, and then you can take finite number of them and then do large volume limit and all that and analyze corrections to a large number of particles. Okay? But you have to organize them in the right way so that those that you miss, that come from finite number of particles, those that you miss are not relevant or less relevant for the physics that you are looking at. Okay? So this is the idea of how you organize this infinite space of conserved quantities. Organize it so that when you have finite number of particles, you restrict to the right subspace, the one that's physically relevant. Yes. Because, of course, when you have finite number of particles, what we mean is that you can still take higher powers, but they become not functionally independent. And they're not new conserved quantities, right? That is the thing, right? But you have a choice of which one you can take. Yeah.
Yeah, so just one more comment, maybe so when I do this discuss the generalized Gibbs ensemble from the quantum field theory point of view, sometimes I find that a good basis for free field theories, a good basis of this conserved charges is the number operator itself. So like a dagger k a k.
Yes.
And then they introduce chemical potentials which are like beta of k
Yes.
times n of k.
Yes.
Then all the relations become particularly simple in
Yes.
that basis. And in that also, I presume that this in a lattice, I'm more familiar with the continuum, but I
Yeah.
believe that in a lattice, the same issue would come because
Yes. Yes.
the number of k, possible k's, is limited by the Brillouin zone. And
Yes, precisely. Yes, yes.
yeah,
So, okay, this is a very good point. Thank you. So let me actually then go into that. So this here was a classical free particles, right? I can do quantum free particle, as you say, right? And then indeed the number operator for momentum k, here I call it p, right, is a conserved quantity. It's conserved and is a good basis of conserved quantity. So let me say, so in the classical case, what it would correspond to, so kind of as a good basis, instead of these powers, right? So this a dagger k in the classical case corresponds simply to these QPs, which are just sum over n delta p minus pn. You just check if the particle of momentum p, how many there are, count number of particle of momentum p. And then Q of Qp of x, the density, is sum over n delta x minus xn delta p minus pn. And indeed, now this looks very nice. So also like in the quantum case, in the classical case, this is also a nice way of expressing the conserved quantities. And then the Boltzmann weight become exponential minus, I put minus by convention, integration dp, some function w of p qp. And it's exactly that function that is involved here. Exactly that. Right? And then we see that indeed we have an infinite space, which is actually a function space. So all the possible relaxed states, they form a space parameterized by a function. And then you can ask what are the good states. Of course, you would like particles of high momenta, you would like that there is not a lot of them. So typically you would ask W of P to go to infinity when P goes to infinity, so that your Boltzmann weight constrain the particles to have finite momenta. Otherwise, you have things that can diverge and all that. But how does it go to infinity? It can go faster, not as fast. It depends on the problem, actually. And the question of what function space, it's a question, depends on the problem. Yeah. So this is the equivalent of the A dagger KAK in the quantum case. So you can do the free classical particle. And this is a good basis indeed. Right? Yeah, other questions? So I would like then perhaps to continue with this basis and ask about what are the hydrodynamic equations that I obtain by naively applying the local thermalization idea to these free particles. Okay, so for this, I have to calculate the average QP of X in this state now that depends on W, which I had denoted by this. So the state that depends on this vector of beta, well, now I call it state that depends on W because it's actually more natural to think of it as a state that depends on a function, much like this, with that Boltzmann weight. Okay. And I have to calculate the current. I can put that. I can put them as 0. So I just take away the position. I can put it at 0x and 0 time, right? According to the general principle. So I have to calculate the current. Now, what are the currents? Well, the currents are relatively simple. You just have to take the derivative with respect to time of this, with respect to time of this, and you find that there's an x dot that will appear there with a derivative with a minus, and x dot is equal to p, so that's x dot n. X dot n is equal to pn, and pn is equal to p. So you find that jp, take this away, jp is nothing else but p times QP of x. So in fact, the current observables are simply expressed in terms of the density observables. This is kind of a trivial computation, but okay, it's correct computation. And as a consequence, the average current, they take the form of P times the average densities. Now, let me denote rho of x and p to be the average density QP. The rho of let's say x, p, and t. The average density QP in the state W that now depends on x and t via the hydro local relaxation principle. So I know that in general, for any state characterized by function W, generalized Gibbs principle characterized by function W, the average currents are P times the average densities. Now I use my local relaxation principle. If I do a little picture, right, I have x, t. So here I have some W of x and t. And W, remember, is a function. I don't write the P here. Maybe I should put where I put my P. I think I'll put it before Pxt, something like that. Pxt. This is actually a function of P, right? So this is W of P, X, and T. So P maps to W of Pxt. So the Wxt is this. It's a function of P, because I need a function to characterize the state. Not 3 parameter, beta, mu, v, but the whole function of momentum. Okay? But that function depends on where you look. So here, there's a function. There's a function, another function. W, so now it's at a different point, x prime, t prime. So this is P mapping to W of P, x prime, t prime. In other words, really, I have a function of 3 real parameters. The momentum to characterize the local state, and the x and t to characterize where I look, where I look to observe the local state. Okay? So this is so instead of a xt and a number, it's xt and a real parameter. So it's 3 real parameters. Okay? And then as a consequence, I define then my densities rho to be the average of the QPs in that xt dependent state. And I said that the current are just obtained by multiplying by p. So these are p rho of p x t. So now if I do that, you see this is all hydrodynamic principle, right? Here have hydro local relaxation, GGEs of free particles, hydro local relaxation tells me that locally I have a GGE is characterized by a function. Okay? And sorry, it's noise. And now I can write the hydro equation. What's the hydro equation? Well, it's dt of all these qi that depend on these betas of xt plus dx of this current ji that depend on all the betas xt. Okay? That becomes dt of qp, right? That depends on the function w of xt plus dx of jp. That depends on the function w of xt. Just changing notation, it's the same idea, right? Instead of vectors of beta have a function, the vector of beta are just the Taylor coefficient of the function w as a function of momentum. Okay, but it's better to use a function w, and then I write this in terms of my definition rho and the current j. So that becomes dt rho of pxt plus p dx rho of pxt equals 0. This is the hydrodynamic equation for free particles. Now, not ideal gas, but proper free particles, where there's really no interaction, and the hydro assumption is thermalization, generalized thermalization, or relaxation to a generalized Gibbs ensemble. Right? Now, what is this equation? This is an interesting equation. It's a simple one, of course. But do you know what name this equation has? It has a name, has different names. Somebody has an idea what name, a name you can put on that equation. What does it look like? No, nobody wants to try it out. Yeah.
I don't think it's wrong. Yeah, okay. So the only answer was Burger's equation, but I don't think so.
Burger's equation is will have nonlinearities. So okay, well actually maybe maybe it's my notation, my handwriting, right? So here's a rho, right? This is a density rho. This is density rho, and this is the momentum p, right? So this is p, which is not rho notation. So there's a density rho that depends on pxt, and there's a momentum p. Other attempt.
Yeah, anyone wants to say no?
So yeah. So let me tell you, you can go see in books. People have called that different things, but it is called someplace Liouville equation. Liouville equation. There's many Liouville equations actually. But Liouville equation for conservation of phase space. If you have a free particle with some distribution over phase space and you evolve it in time, it turns out that phase space element dxdp is conserved. There's an equation for this conservation, and this is that equation. Also is being called collisionless Boltzmann equation. So Boltzmann started with Liouville equation for conservation of phase space element. Phase space element, let's see. You start with Liouville equation for conservation of phase space element, which is what you would expect if you have a lot of particles with some distribution of particles. They are all independent, some distribution, and they go around. And so that distribution evolves in a certain way, and naturally, so it's that way. And then add the collision term, so something that changes the densities in phase space due to momentum changing at collision, right? Add the collision term. If you take away the collision term, you get back to this Liouville equation. Boltzmann wrote it in a dynamical way. And so in other words, this is so-called kinetic theory of gases. But a really, really simple case of kinetic theory of gases is the case of free particle. It's kinetic theory. So in other words, this is a very, very well-known equation, right? So indeed, it is true that if you take free particles with some distribution in space at initial time and also in momentum, and then evolve them, they will satisfy that equation. People knew that a long time ago. Boltzmann knew that and added a collision term to that to represent interaction. But he knew that if there was no interaction, this is it, right? That's the equation. And what we did here, which I think is conceptually interesting, is that we reobtained this equation from kinetic theory, kind of started by Boltzmann or kind of around that, Maxwell and Boltzmann, kinetic theory. We reinterpret it in terms of hydrodynamics, in terms of emergent hydrodynamics, not the original equations of hydro that Euler wrote, right, for interacting fluids and gases, but the notion of an emergent equation at large scales that emerges from microscopic degrees of freedom, particles interacting with each other, emergent hydrodynamics. And how we did that? We did that by slightly, just at one point, only one point in the derivation of hydrodynamics as an emergent theory, at one point only, we made a modification. And this one point is where we consider the states towards which the system relaxes. There, we extended that. We extended the set of states towards which the system relaxes by taking into account all the conserved quantities emitted by the free particle models. Just by doing that, we reobtained kinetic theory of gas for free particles. So it's a different interpretation of kinetic theory of gas. So it looks like it's the right thing to do, because we know that it's the right equation, the kinetic theory of gas. So it looks like it's the right thing to do to extend the set of states by including all conserved quantities. So this is that example. Now, one thing that is important here, very important thing, is that, you see, I said when I write, I forgot to put 0 here, right? Equals 0. Okay. When I write that equation there, this is the hydrodynamic equation for a generic system. No matter how many conserved quantities, and it's hydro equation. So this is kind of a generic Euler scale hydro equation. Okay. I wrote that. Okay. And in this hydro equation, somehow the only data that I need from the system, the only data that is needed is the values of the currents, the values of these average currents in all the states admitting all the conserved quantities. Right? So all the stationary states which admit all the conserved quantities. So I need to know what are the conserved quantities first. I need to have the full set of conserved quantities, then construct the states with the Boltzmann weight controlled by these conserved quantities. Then I need to calculate the currents. Well, okay, I also need to calculate the densities as functions of the betas. And then I write this as an equation for states that vary in space-time. So for betas that vary in space-time. But wait a minute, what did I do here? Here, I said the currents are just P times the density. So actually, I never had to calculate the average densities as function of the state W. I recast the description of the state. Instead of using the generalized temperature or the function W, I use the densities themselves, the average densities themselves. So in fact, all I need is the currents, these currents, as functions of the densities. And once I write them as function of the densities, I can indeed write an equation for the evolution of densities. Right? So here I see the general principle. First, determine all conserved quantities. I have to tell you a bit more what are these conserved quantities. I'll come to that just now. What does it mean, all? I put in quote for now. First, determine all conserved quantities. Second, construct all the stationary states. Stationary states. So I call them QI, right? With these conserved quantities. So these have Boltzmann weight which are the form exponential, put a minus by convention, you put parameter beta I, put your QI. I tell you just the Boltzmann weight, the explicit form of the state depends on the statistics, classical, quantum, bosonic, fermionic, and depends on the form of the interaction. But okay, so once you have that, this is the Boltzmann weight that you have to put. 3, evaluate all currents JIs. But here, the correct thing to do is evaluate the currents as I did here. Evaluated the currents as I did here, as function of the densities. So I say evaluate all GI as functions of of the densities Q, okay, for K equals 0, 1, 2, 3, all the densities. Okay. So this function usually, I mean, I may denote it as a capital J. It's a function of all the Q's. So I put a underline here to say it's a vector of all the Q's, which self depends on all the betas, right? So evaluate the currents as function of density. And 4, write the Hydro equation. dt of these conserved densities, Qi, plus dx of currents, Ji, as function of conserved densities, where the overline is just the average of conserved densities in this state, depending on beta. So I get rid of the beta characterization, and I characterize the state in terms of conserved densities. And then I have this equation. And this is the general form of the Euler hydrodynamic equation. It's what I did then for the free particles. Free particles, I obtained that one there. So these are the general principles for Euler hydrodynamics. And the equation here in the square is the generic Euler scale equation for a many-body system. And that equation, once you've determined the correct set of conserved quantities, correct space of states, it's extremely general. It's supposed to be applicable to almost every locally enough interacting many-body system. It is extremely general. The system may be integrable or not, may be Hamiltonian or not, may be stochastic, may be quantum, may be classical. It appears to be extraordinarily universal. All you need to know in order to get a dynamical equation at large scale is the currents as functional densities. Okay, so some questions about this form equation and what I've said till now.
Benjamin, so now you're going to write it in that kind of Boltzmann form, or?
So yeah, so exactly. So the Boltzmann form. So this is the generic one. Okay, for free particles, we had the mapping I becomes P. So instead of looking at conserved quantity 0, 1, 2, 3, we use this continuum of conserved quantity that Gautam talked about, right? This A dagger PAP, which is this QP. Okay? So I becomes P. Then, and Q bar I, that depends on X and T, then becomes rho of P X T. Okay? Ji of all these Q average, and whole vector of them, becomes just P rho of P X T. And then once you put it in there, you get the kinetic equation. So that's the mapping between these things, okay? For the free particle. Okay. But this is more general. So in general, you get something different depending on the model. For interacting models, for interacting, let's say, non-integrable Galilean models, where you have I takes value 0, 1, 2, and the Ji's, so J0 of all these Q's becomes just, as a function of Q's, become Q1 average. J1 of all these Q's, this is the current to momentum, becomes a function pressure that depends on the model you have to calculate. Function of Q0, Q2 plus Q1 square over Q0. And J2 becomes 3 Q1 average over 2 Q0 times that function plus Q1 cube over Q0 square. And then you just have Q0 xt, Q1 xt, and Q3 xt. These are your dynamical variable, things that evolve. And using these currents, you get the standard form of the hydrodynamic equation for interacting non-integrable Galilean models. So these are two examples where this general form of the hydro equation specializes to known forms of large-scale evolution equation. For free particle is kinetic theory, cohesionless Boltzmann equation. For interacting non-integrable Galilean particles, it's a standard Euler equation, conservation of mass, and conservation of energy equation. They all fall within that general class of equation. Okay. Yeah, so clarify.
Sorry, Benjamin, can I ask?
Yeah.
Yeah, so the just to understand the last set of equations which you get from the Galilean invariance, here basically you get it by shifting the momentum by Q1 bar. So you write momentum is equal to Q1 bar plus momentum.
That's right. Yes. Yes.
Yeah. Okay.
Yeah. Exactly. It's just that. Yeah. Exactly.
Yeah.
So because in this case, yeah, exactly. So and it works in general. Of course, you have to for the general Galilean invariant system, you have to properly see what this shift of momentum does on your currents and densities. But it comes out from, if you wish, from the general algebra of Galilean transformations in classical particle system or in quantum particle system, right? There's a Galilean boost that you can write explicitly, and you use the algebra that combines Hamiltonian momentum, Galilean boost, and number of particles, and then you get this equation. So so there's a bit of calculation that you can do, but using this algebra, you can get this equation. So you use the algebra directly on the observables themselves, and then you deduce what you get for the averages. Yeah.
Nice.
Yeah. Yeah. Other questions? Okay. Now, so this is a general theory, and I think it's for me, I think it's very beautiful because that connects two things which appear completely disconnected, which in standard textbook they will say they have nothing to do. One of them is free particles, where there is no interaction, and when there's no interaction, it's kinetic theory, and that's it. The other is in interacting particles, Galilean invariance. There's interaction. Then the textbook will tell you, well, you have to introduce interaction. You have to modify kinetic theory, add Boltzmann collision terms. But Boltzmann collision term is just an approximation because they just take into account two-body collisions. It's kind of a low-density approximation. Maybe from that you can do calculation and then get at least an approximation of the standard Euler equation, right, for Galilean system. So what I'm saying is actually these two equations, they both come from the same general principle of hydrodynamics, which is local relaxation to the set of stationary states admitted by a system, and then evolution controlled by conservation laws. Both come from the same principle, which I think is kind of interesting. Okay, so now the idea now is relatively simple, right? I did free particles, I did interacting non-integrable Galilean models. And when I said here non-integrable, what I meant is simply that there's no other conserved quantities than Hamiltonian number of particle momentum. That's what I mean there, right? So, what does it mean to be non-integrable? So it's my definition. But then I have to tell you a little bit more. Then it is clear from that it's clear how to do integrable models, right? You just have to apply the same principle, same general equation, that equation, and then just apply it to the infinite set of conserved quantities of integrable models. And again, as it was mentioned, it's infinite because we consider a priori system to be infinitely large, infinite number of particles. So you have to just write all the, you have to apply these 4 steps to integrable model. Determine all the conserved quantities. Okay, I mean, there are books on integral model that do that, right? They write conserved quantities for you. So it's kind of done, if you wish, right? Construct all the stationary states. Well, these are the GGEs. So again, there's a lot of work on that. So people have done that. GGEs are known, done. So 1, 2, done. Okay. Evaluate the currents as function of densities. That is a bit more difficult. So this, you see, before people started developing GHD, generalized hydrodynamics, the first 2.1 and 2, this one and this one, they were perfectly known and perfectly done. And a lot of people knew about these 4 steps. People knew that this was the way, right? But people did not know how to evaluate the currents. So these things. So this was the complicated stuff. Okay? Evaluate the currents, the average currents, function of densities. For free particles is simple. Now we know, so there are various techniques. Okay? But once this is known, then we could write immediately the hydro equation, because it's just a matter of putting these currents into that equation and get something. And then it's a matter of analyzing that equation and see what it gives, how it's interpreted and all that. And very interestingly, in an integrable system, that equation is essentially in between the free particle case and the interacting Galilean case. It's kind of in between. It's like free particles because there's an infinite number of conserved quantities and you can use momentum and all that. But it's not true. This expression of the current is much more complicated. It's not linear, and the conserved densities in the row is more complicated. And then so there are nonlinearities, much like here. So here, the currents are nonlinear functions of the Q bars, right? Like you have here Q square over Q0, right? So it's nonlinear function. Like here is linear, you just have rho, right? And this is linear is particularity of free. Nonlinear is when you have interacting. Integral systems are interacting, so become nonlinear. So but they have structure of a Liouville equation a little bit. And so they're in between. And that's kind of interesting part. Okay. So this is the point. Now this is what we should do. Okay. Now, before I do that, let me say a little bit more about point 1, 2, 3. Because there's a question of what are all these conserved quantities? What does it mean, all conserved quantities? What are the stationary states? How do I construct these? I mean, you know what they should involve, but how I make sure that I got all the conserved quantities, for instance? And then evaluate currents as functions of densities. What are these functions of densities? Currents as functions. What do they look like? These functions, right? The constraint on that. So these are the 3 things that I want to discuss before I get to integrable model. So I discuss that for the rest of this class. Then I have 15 minutes. So I start discussing that for the rest of this class, and I continue for the next class. And then I will introduce integral models next class, and hopefully get to the GHG question maybe tomorrow, maybe the day after. Okay. So before going to integral models, we kind of see now the path. I want to explain the general principles behind that, because it's actually crucial also for integral models. Right? It's crucial to know what the general principles are so that we get the right set of states, for instance. Okay. Okay. So this is that. Okay. So general principles. So what are the? I will not go too much in detail, but I want to say a few words. What are the conserved quantities? When I say I need all the conserved quantities, what do I mean? Conserved quantities. Well, there is. It appears that there's one important property of these conserved quantities. I mean, maybe a similar question, related question is what are the stationary state? Okay? So what are the principles that guide us to determine the conserved quantities stationary state? So it appears as one important property for conserved quantities. So the important property is that the QIs must be extensive. Now, this is a terminology borrowed from thermodynamics, right? Where you have extensive observables and intensive observables, right? So QI must be extensive. So what it means is that actually it should grow linearly with the size of the system. So QI grows linearly with size of system. So also, because we want to describe stationary state, it should be homogeneous. What does it mean homogeneous? Well, homogeneous in space, so it should look the same everywhere in space. Now, how to explicitly characterize that? Well, essentially, if I put Boltzmann weight exponential minus beta I qi, the result should be time should be space translation invariant. That's homogeneity. And of course, well, I didn't see it even, but QIs must be conserved. So also then mean that the result is also time translation invariant. So you have to have space-time translation invariant. So what you have to have, translation invariant, are charges which are space-time homogeneous and extensive. So extensive is a crucial property here. Grows with system size. Now, grow with system size, well, if you have integration over all of space of a local density, then that grows with the system size. So if I constrain my system to lie between minus L and L, the value of this quantity in a typical ordinary state is going to increase with L. So if I look at the density of energy over a region of size L and this finite density of energy, like in a gas or finite density of particle, then that would increase with L. Okay, that's extensivity, but that's a naive way of extensivity. Okay, there's a more formal way of defining extensivity, and it is following. So given a state, so an average, right, some ensemble, some state, then you can always choose the average of qi to be 0 by shifting it. Okay, you can make it 0 by shifting it. So actually, by just adding the identity observable, just one. Okay, so actually, the saying that it should grow with system size in its average is not so good because you can shift it to have average 0. Of course, you don't want typically to shift the energy, and it should be positive, but formally you can shift it. So if you want the formal definition, just average is not so good. But what you can do is you can look at the cumulant. So Q square C, C for cumulant. And that's the average of Qi square minus the average of Qi square of the average, right? Cumulant. Okay. And then the notion of extensivity that is useful formally for mathematical purposes is that Qi square cumulant should grow like system size. And it turns out that if you indeed evaluate a conserved quantity of this type, then cumulants will grow like system size. So let me go a bit over that, how this grows like system size. And then I tell you maybe some general statement about what we expect are the states towards which a system relaxes at large time in terms of conserved quantity that grows, whose cumulant grow like system size. Okay, so this is extensivity. So example, if I have indeed a conserved quantity of the type, okay, Q is integration dx Q of x, okay, and I put that on a finite system size, say between 0 and L, and I evaluate its cumulant. So Q square cumulant. Okay. Well, that's going to be integration from 0 to L dx, and from 0 to L dx prime, Q of x prime connected, cumulant. So the average of the product minus the product of averages. Okay. Now, this has two integrals over L. How can it grow like system size proportional to system size L? It looks like there are two integrals. It looks like it should be L squared. But in fact, so in states which are such that connected correlation functions, which are cumulant, right? Connected correlation functions vanish fast enough, meaning that Q of x prime connected goes to 0 fast, like exponentially, as x minus x prime goes to infinity. So in such states, then the integral here that I have over x and x prime is going to be supported on the values of x around x prime. And the rest is going to integrate to some just finite contribution. So values when x and x prime are very far from each other are going to give 0. So as a consequence, Q square connected is going to be approximated as L is large by integration, say dx from 0 to L, and integration, say dy, which I integrate from minus infinity to plus infinity of Q of x plus y connected. And that integration over y is finite, just a number that depends on x, does not depend on L anymore, because of this fast decay. So fast decay of correlations then guarantee that the result goes like L, and since if the state is homogeneous, then the result does not depend on x. So by homogeneity, goes like L times the integration over y of Q of 0, Q of y connected, which is finite. L times this, and this thing is finite if there's fast enough decay. So then the general theory is the following. So in typical Gibbs state, equilibrium states, it turns out that correlations indeed decay fast enough. So when you look at local observables which are far from each other, because of temperature, because of fluctuations, these observables don't know about each other. So the correlation, which is the value of the cumulant, the connected correlation function, decay fast enough. And then you can integrate and you get the cumulant Q square, and then you find then that something that looks like an integration over a extensive region, its cumulant grow like the region. Right? So the general theory of conserved quantities is as follows. Given a state with fast decaying correlation function, connected correlation functions, you look for all observables, can be, operators, or observables of phase space, Q, which you can constrain to finite system size, such that Q dot is 0, such that they are homogeneous. One can make in space, one can make a precise statement about that, and such that the average of Q square connected in that state grows like system size. These are observables. Okay, this set of observables is the set of extensive conserved quantities, and these are the observables that you must put in the exponential to construct the stationary state. So then you can, so the proper way of doing that is you can modify the state as say you put a beta as inserting this Q and normalizing, and that new state is going to be within the correct space of stationary states that are obtained from relaxation. So the new state still has decaying correlations. I can't write. And is within the set of state that you obtain after relaxation. And typically, you would start with, maybe in quantum case, you start with the trace state. Which has, of course, decaying correlation. And then on that trace state, you construct all these conserved quantities which have linear in system size second cumulant. And then the state of that form are your generalized Gibbs ensemble, where you can put here any one of these charges which grow like system size. Right? Now, the set of charges that grow like system size actually form a Hilbert space. You can take a basis, and what I denoted by Qi before should be understood as a basis within this Hilbert space. And you put in the exponential, this beta IQI is just a decomposition within that basis of an extensive conserved quantity whose cumulant grows like system size. Right? So this is kind of the general theory, and you can make it precise in quantum spin chains in particular, where you have a general theory of stationary states in terms of extensive conserved quantities. Right? Now the thing is a bit formal, but it's important. In particular, in Heisenberg spin chain, for instance, it was discovered by Tomasz Prosen and his group that the conserved quantities which had been written previously, they were not enough to fully cover that space, the space of quantities which are conserved in time, homogeneous in space, and whose second cumulant grows like synthesized. There were more, and they discovered what are these other conserved quantities, and they are crucial in relaxation, in the study of relaxation. It's crucial to put them within these exponential, within a Boltzmann weight, to get the correct set of all relaxed states. So this was a kind of an important discovery in integrability, but it's a more general principle. So this is kind of what these conserved quantities should be. So if you just look then at the momentum of a single particle, that's not enough. That does not grow like synthesized because the single particle is just in one point in the system. So that will not be a good conserved quantity to describe your Gibbs state. So you have to look at the momentum of all the particles within a region, and then that will be a good conserved quantity. So yeah, okay. So I don't want to say too much more about this, but this is an important principle, and this space of conserved quantities. Well, it was originally called conserved quantities which satisfy this property there, were originally called pseudo-local. Right now we understand them as simply being extensive, but it goes beyond the naive extensivity principle. You have to look at all the conserved quantities that satisfy this relation, and there may be more than those you thought you had. So there are some of them whose local density may be supported on many sites, but perhaps with exponentially decaying amplitude, such that still second cumulant grows like system size. Okay? And these have to be included in the generalized Gibbs ensemble. Okay, so this is a bit formal, but it's important. So connect with, just one last thing to say, that it connects with Prosen's pseudo-local charges and his discovery that these are important for thermalization phenomena and relaxation phenomena. So we have to include them also in hydrodynamics. Yeah. Okay, so this is what I wanted to say, and I want to say this kind of covers a bit point 1 and 2 here, right? Description of what are these states and what are these charges, just a little bit. And the next lecture, I'm going to discuss what are these functions gi of q, what properties they have, and then I'm going to apply this whole principle to integrable systems. Go back here, go back there. That's it. Okay, sorry I went a bit over. Thank you for your attention. Any question, do let me know.
Yeah, Benjamin, I have just a couple of questions. So one is, I guess in classical systems, like this, finding the n constants is more cleaner, right? That it's more straightforward. There's no ambiguity.
Yeah. I mean, there is still the principle. You see, this definition of this extensive Q, you can still do that in classical system, right? You don't have trace state, but you can take a state, a Gibbs state or whatever, some state, okay, that you know, that you control, that you have, which you know has exponentially decaying correlations, and look for all conserved quantities whose second cumulant is extensive. In fact, the proper thing is that all the cumulants, not just second, all the cumulants should be extensive, but okay, it's sufficient to think about the second cumulant. Look for all of these, and then those that you well, in free particle system, those that you write in terms of W they are of that type, and that gives you some kind of constraint on what kind of function can be associated with these kinds of quantity, right? So you get constraint on the function space. Right? And if you have classical interacting systems, this is still a non-trivial question. And as far as I understand, it hasn't really been properly answered in general. Like take a classical two-dot chain. We know the concept of quantities, we know, and those that we write, they are probably correct, and that's it. But hasn't been properly answered that those that we write cover the full Hilbert space of extensive
You're
concept
saying
quantity.
even for Toda, it's not clear? That's what you'd say?
Yeah. It hasn't. I mean, I'm pretty sure because, you do numerics and everything works, right? It's because of that, right? But from the principal point of view, it hasn't been shown that these kinds of quantities that we talk about cover this full Hilbert space. Yet, the general results, like more mathematically rigorous result that you can get about thermalization, they always involve the full space of such concept quantities, right? You define a space which have this property, that property, that property, and then you prove stuff with that space. Like you can prove linearize the Euler equation with that space. And so whatever charge that in that space is involved. And in Toda model, we haven't shown that those that we write from the full thing, although I'm convinced that they're correct, right? So the question here is about completeness. Do we have all of the charges?
Okay, but like for classical system, at least there's a, like in terms of action angle variables, there's a clear notion of...
This is correct. So, and this is the second question. In terms of action angle variable, there's a clear understanding of completeness. And that's it, right? So it should be that, right? I agree. But this is a bit different. So here's how it's different, right? So in terms of action angle variables, you take a finite number of particles. This was the question, right, that Gautam asked, right? You take finite number of particles, you have a finite number of them, and then completeness is no ambiguity. Here, I must take infinite volume size. In fact, the proper formulation of this whole thing is within a context where you immediately have an infinite number of particles. And then you construct a sequence of charges which are supported on larger and larger and larger intervals. And then you ask for that type of scaling. Okay? And the question is, the charges that you construct now, they are really just a subset of all these charges that you have when you have an infinite system. Because you have an infinite system, you just have a huge amount of very weird charges all over the place. Some of them are not extensive, some are just really weird. They're still, they're complete from the point of view of action angle variables. You have something different here. Yes, for extensive. So it's kind of a subset of all the charges that you would have in a truly infinite system. Or more precisely, as you take the limit to infinite system, you have to take appropriate limits of conserved quantities. And these will be the correct one. And it's not clear, hasn't been established that, or even precisely formulated, what is this correct subset, right? So this is a different completeness from the one of action angle variable. And that completeness is actually more relevant to thermalization in infinite system. That is the one that's relevant. This one is not the action angle variable one. It's this one. That completeness is the one that's relevant for thermalization for hydrodynamics. And it's different. So yeah, there's still something missing.
Okay, thanks. Any other questions?
Sorry, can I just ask a very short question? So, suppose I have a system which is, again, using a little bit of QFT kind of language. Suppose it's has long-range interactions, and so like gapless. Then, of course, the state can correspond to some high-temperature state, so that I can still ensure a short-range correlation, like the QX prime connected could be short range. but it's a little, state-dependent definition of the extensivity, in the sense that if I'm near the ground state, then this cumulant, will have maybe some log stuff or something. So it will not satisfy this precise proportionality to L.
Yeah, correct. So thank you so much for the question, because I didn't have time to go that, but indeed this definition is state dependent. So actually, I do a little picture here. What you have is some kind of a manifold of state. Given a state, say if hyperpage state is a point in that manifold, you have some direction of modification of that state. And these are the extensive charges. So the charges, their Hilbert space is a tangent space, that manifold of state. And that space depends where you are. So they can be, of course, like a singular points, exactly as you say. Singular point where suddenly set of extensive charges change. And I don't know, right? I don't know how it affects hydrodynamics. I mean, there's not much to develop, but like formally, that's the case, that you can suddenly have more or less extensive charges, and that would affect the dynamics. Perhaps, going to that point will take more time, things like that, right? So so the proper thing is that these extensive charges, they form a Hilbert space, and that's a tangent, the manifold of stationary states. And the whole thing is about studying that manifold, its structure, and the tangent space everywhere, and how the system moves around that manifold.
Nice, thank you.
Other questions?
Yeah, I think no other questions. Yeah.
Okay, thank you very much. Should I provide, so there was a little kind of calculation that one can do. Should I provide some separate file with this particular problem, maybe, that people can have a look at it?
Yeah. You can just send it to me, then I'll.
Yeah. Okay. Excellent. Yeah. I'll do that.
I guess if you want, like, you have many lecture notes. If you maybe you can specify like any particular one which might be useful for to.
Yeah, indeed. Yeah, I'll do that. Yeah, exactly. Yeah, I'll do that. Very good. So
Okay, thanks. Yeah.
I'll try to do that now. Okay, excellent. Thank you very much.
Bye.
See you tomorrow.